Imagine you're at 30,000 feet. Everything is normal. The hum of the engines is a background lullaby. The cabin is warm, and the clouds look like endless fields of cotton. Then it happens. Silence. Absolute heart-stopping silence. Both jet engines have flamed out. In a heartbeat, a 200-ton hunk of high-tech engineering has just turned into the world's heaviest wireless kite. This isn't a scene from a disaster movie. This is the cold, hard reality of a ditching, an emergency landing on water. Now, landing on water sounds almost poetic, doesn't it? Like skipping a flat stone across a pond? But the physics tell a much more violent story. At these speeds, hitting the ocean isn't like hitting a liquid. It's exactly like slamming into a solid, reinforced brick wall at 124 miles per hour. This is the ultimate test of human skill and mechanical integrity. If the pilot's approach angle is off by just one single solitary degree, the fuselage doesn't glide, it shatters. It disintegrates like a crystal vase dropped onto a concrete floor. There is no room for almost. There is no close enough. Otherwise, the people inside simply won't make it out. So, how do you do it? How do you transform the unforgiving, chaotic surface of the ocean into a life-saving runway? To understand how we survive the impossible, we have to look at the rigid, step-by-step protocol that turns a catastrophe into a manageable mission. This is step 1, the Earth departure equivalent, the cabin lockdown. When the cockpit realizes the engines aren't coming back, flight attendants begin a highly orchestrated survival dance. This isn't just about shouting instructions, it's about physics. When they yell, "Brace, brace," they are commanding you to lock your body into a specific geometric position. By leaning forward and pressing your head against the seat in front of you, you are lowering your center of gravity and minimizing the secondary impact force. In a crash, your body wants to keep moving at 150 miles per hour even when the plane stops. Bracing ensures you are part of the plane's structure, using the seat's frame to absorb the energy that would otherwise snap human bone. While you're bracing, the pilots are performing step 2, the glide profile. This is the aviation version of a translunar injection. Without engines, the wings are the only fuel the pilots have left. Every foot of altitude is a precious currency that must be traded for distance. The pilot is hunting for the angle of attack, that razor-thin margin where the air still flows over the wings just enough to keep the aircraft flying at the slowest possible speed without stalling. It is a terrifying balancing act. If they fly too fast, the plane will skip off the water like a pebble, tumbling end over end until it breaks apart. If they fly too slow, the plane stalls and drops like a lead weight, belly flopping with enough force to cave in the floor. Then comes the most critical technical maneuver, step 3, the configuration. Modern aircraft are equipped with a secret weapon known as the ditching switch. Deep in the overhead panels or on the center pedestal, this single button does something remarkable. With one press, the aircraft's onboard computers take control of every opening under the waterline. It slams shut the outflow valves, the air conditioning ram air intakes, and the avionics cooling vents. For a few desperate minutes, the aircraft is no longer a flying machine. It is a sealed, pressurized hull. It becomes a temporary boat, designed to stay afloat just long enough for the souls on board to escape. But even with every switch flipped and every angle perfect, the ocean is not a laboratory. It is a chaotic, living beast. What happens when the perfect engineering plan meets the reality of a 3-story wave? In a simulation, the water is a mirror. In the real world, it is a churning graveyard of whitecaps and hidden currents. This is where the ideal meets the catastrophic. You can have the most experienced pilots in the world, but if a single sensor fails, the mission is over. Think about the recent headlines regarding the Starliner and its helium leaks. Even a microscopic failure in a pressurized system can lead to a near-fatal disaster. On a commercial jet, it might be a cargo door that fails to latch properly, or a pressure sensor that gives a false reading. Imagine the pilot nails the landing. The plane remains intact, but the sheer force of the water jams the emergency exits shut. Suddenly, that 90-second golden window for survival starts shrinking. Under the crushing pressure of the sea, crack no wider than your finger can let in enough water to turn a state-of-the-art cabin into an iron coffin in a matter of seconds. The friction isn't just a force, it's a weapon. The water doesn't just splash against the hull, it slams into it with the concentrated power of 1,000 sledgehammers hitting it once. But this is why we rely on the logic of redundancy. Aviation engineering is built on the principle that if one thing fails, something else is already waiting to take its place. Much like how a Falcon 9 rocket uses 9 Merlin engines to ensure that even if one explodes, the mission continues. A modern airliner is a fortress of fail-safes. Look at the evacuation slides. These aren't just inflatable ramps, they are sophisticated self-deploying life rafts. They come equipped with survival kits, radar reflectors, and insulated canopies. The crew is trained to act as a singular, high-performance unit, clearing a path through the chaos while the plane is still pitching in the swells. And then there is the airframe itself. We now build planes using advanced carbon fiber composites and high-strength alloys that can withstand extreme bending and impact forces that would have snapped the metal planes of 50 years ago. This is the final shield, a structure designed to endure the unsurvivable so that the people inside don't have to. Now, let's look at the moment of impact. When that belly hits the water, the resistance creates a massive, violent deceleration, a blackout of momentum. It is the aviation version of a spacecraft's fiery plasma wake during re-entry. Inside the cabin, it is pure, unadulterated chaos. The lights flicker and die. The roar of the ocean rushing past the windows is deafening. This is when the 90-second rule begins. Every airline in the world must prove that they can evacuate a full plane in under a minute and a half, even with half the exits unusable. And here is a detail that saves lives, but most people forget in the heat of the moment. Never inflate your life vest inside the plane. If the cabin fills with water, an inflated vest will pin you against the ceiling like a cork, making it impossible to swim through the door. It is these tiny, counterintuitive step 4 details that determine who walks away. Once you're in the rafts, the transition to rescue begins. Just like the US Navy recovery ships waiting for an Orion capsule to splash down, the global search and rescue network is already moving. Long-range drones and satellites track the aircraft's last known coordinates, and rescue teams are often dispatched before the plane even touches the water. To give you an idea of the sheer scale of what we're talking about, the force of a water landing is equivalent to taking 50 fully loaded school buses and dropping them from the top of a 10-story building simultaneously. It is a testament to human ingenuity that we can survive such a thing at all. But in the world of high-stakes engineering, miracles aren't magic. They are just physics that have been mastered. Nothing is left to chance. Every rivet, every ditching switch, and every brace command is a calculated defense against a catastrophic end. We make these original, human-animated breakdowns from scratch to decode the complex mysteries behind the headlines. If you want to see how the world's most complex machines survive the impossible, hit that subscribe button and join our team of decoders. But here's the problem. In a flight simulator, the water is a perfect, flat mirror. It's a mathematical ideal, a calm surface where every variable is controlled. But the real world, the real ocean, is a living, breathing, and utterly chaotic beast that doesn't care about your flight plan or your carefully calculated approach. Imagine slamming into a 3-story wall of churning salt water while traveling at 140 miles per hour. As the fuselage skips across the swells, the physical forces at play are nothing short of catastrophic. This is where the gap between perfect engineering and brutal reality becomes a literal death trap. Even if the pilot nails the descent, the sea has its own ideas. Consider the recent high-stakes drama with the Boeing Starliner and its notorious helium leaks. In the vacuum of space, a tiny pressure drop is a mission-ending crisis. In a water landing, a single faulty sensor can be a death sentence for everyone on board. If the aircraft's onboard computer miscalculates the distance to the whitecaps by just a few feet, perhaps because of a salt-crusted probe or a sudden glitch in the radar altimeter, the plane doesn't glide. It nosedives. It slams into the water with enough kinetic energy to liquefy the internal floor structures and shear the wings right off the mounts. And even if you survive that initial bone-shattering impact, the nightmare is only just beginning. The pressure of the ocean at even shallow depths is staggering. Think about a crack in the hull no wider than your pinky finger. Under the crushing weight of the Atlantic, that tiny gap becomes a high-pressure fire hose, unleashing a torrent of freezing water that can fill a cabin in a matter of seconds. And then there are the exits. Emergency doors are designed to pop open effortlessly on a sunny tarmac, but under the weight of several tons of seawater pressing against the fuselage, they can become physically jammed shut. Suddenly, that state-of-the-art aluminum tube isn't a life-saving vessel anymore. It becomes an iron coffin, sinking into the dark, silent void of the deep before anyone has the chance to even unbuckle their seatbelts. This is the moment where every passenger realizes just how thin the line is between a controlled ditching and a total loss of life. It's a terrifying, heart-pounding race against a clock that is ticking entirely underwater, where the physics of the ocean are actively trying to keep you inside. But engineers don't leave your survival to luck. They build fortresses out of logic and redundancy. If the aircraft's fuselage is the shield, then the backup systems are the sword. Think about how SpaceX designs the Falcon 9 rocket. It's powered by 9 Merlin engines for a very specific, life-saving reason. If one engine fails or explodes during the ascent into orbit, the other 8 simply work harder to compensate. The mission doesn't fail, it adapts. Aviation safety operates on that exact same fail-safe philosophy. Take the evacuation slides, for example. These are not just yellow inflatable ramps used for a quick exit. In a water landing, they are high-tech, self-righting floating fortresses. Each slide raft is equipped with its own survival kit: radar reflectors, GPS beacons, and insulated canopies designed to keep you alive in the middle of a winter storm or a scorching sun. And they are fast. They have to be. Because in a ditching, the crew is operating on a hair trigger. Every second is a piece of code being executed by humans who have practiced these maneuvers thousands of times. They move with the precision of a Swiss watch, clearing paths and deploying rafts before the water even reaches the floorboards. Then there is the airframe itself. We have moved past the era of simple metal shells. Modern airliners are increasingly built using advanced carbon fiber composites materials that are significantly lighter than aluminum, but orders of magnitude tougher. These composites can absorb massive amounts of kinetic energy, flexing under the violent impact of a wave instead of shattering like glass. They are designed to stay intact under structural loads that would have crumpled a plane from 40 years ago. This is the ultimate safe zone. It is a multi-layered defense system where material science, mechanical redundancy, and human training all converge into a single, unbreakable goal, making sure that when the worst happens, the system is more reliable than the catastrophe it is facing. Every rivet and every backup circuit is a silent guardian waiting for a moment we hope never comes. Think about the absolute peak of the crisis, the moment of impact. When that massive belly finally meets the ocean surface, the drag isn't just a splash. It is a violent, earth-shattering deceleration. In the space industry, astronauts experience a plasma wake as they tear through the atmosphere. For a pilot in a ditching, this is your version of that fire. The aircraft slams into the water, and for a split second, the laws of physics are the only thing in command. Kinetic energy is being converted into raw, destructive force at a rate that would buckle almost any other structure on Earth. Then the blackout hits. Inside the cabin, the main power systems fail. The lights flicker and die, leaving only the dim red glow of emergency floor path markers. The roar of the water rushing against the fuselage is absolutely deafening, a sound that feels more like an explosion than a landing. This is the exact moment when the 90-second rule begins. Federal regulations are cold and uncompromising. Every commercial aircraft must be capable of being fully evacuated in under a minute and a half, even with half the exits blocked or submerged. Why 90 seconds? Because that is the estimated time it takes for the internal pressure to shift or for the structure to lose its buoyancy. In the middle of this chaos, there is one tiny, counterintuitive detail that saves lives. But in the panic, it's the one thing most people get wrong. You must never, under any circumstances, inflate your life vest while you're still inside the cabin. Think about the physics. If the water starts rising and your vest is full of air, you become a cork. You will be pinned against the ceiling of the plane, unable to dive down to reach the door or swim through the exit. You will be trapped by the very thing meant to save you. It is these microscopic technicalities, the dry logic of safety manuals, that separate a tragedy from a miracle. As the cabin crew executes their evacuation protocols with surgical precision, the rescue phase is already moving at light speed. Just like the US Navy recovery ships waiting in the Pacific for an Orion capsule to splash down, a global network of satellites, long-range search drones, and Coast Guard cutters is already closing in. Your last known coordinates were broadcast the moment the engines failed. In the world of aviation, you are never truly alone, even in the middle of a dark, silent void. To put the scale of this into perspective, hitting the water at these speeds is equivalent to taking 50 fully loaded school buses and dropping them from the top of a 10-story building all at once. It sounds like an unsurvivable catastrophe, but in the world of aviation, safety isn't a matter of luck. It's a series of brilliant, calculated, and invisible engineering victories. Every soul that walks away is a testament to the dry math that protects us. We are a small team of animators dedicated to decoding the world's most complex engineering mysteries from scratch. Hit that subscribe button to join us as we decode the next one.